a problem here, since the segments of the same word type probably share the same or pretty similar underlying subword sequence or acoustic unit sequence if we use an AUD model. But however, here the AUD model gives different acoustic units even for the tokens with the same word identity. So we like to solve this problem. Since we are in the condition of no transcribed speech, no pronunciation lexicons, we look for weak supervision. And the goal here is to bootstrap acoustic modeling with weak supervision. And we take the assumption that long word or phrase-sized acoustic patterns are easier to identify than frame-level or phoneme-sized ones. We're going to take the approach to exploit the partial labels in the form of pairs or clusters of speech segments that share the same unspecified word type. And if we think of the example word greasy, and there are 3 tokens in the corpus, and we like to group these 3 tokens together and cluster the acoustic segments and use these segments to update the model. But actually, when we group these tokens, we don't really need to know these tokens are the word greasy. We only need to know these tokens are of the same word type. And in this case, it makes obtaining these partial labels feasible in the zero resource setting. So we see these labels can come from a spoken word discovery system. Recall in the past few years, there have been a number of efforts to developing automatic approaches to discovering the repeated words and phrases in the speech corpora using only the raw acoustic features. When we apply the segmental DTW to the corpora, it can retrieve the repeated words and phrases that can serve as the training examples we need here. And these acoustic segments retrieved can also be verified by a human listener who may not really need to understand this language. They only need to listen to these segments and verify if these segments should be the same word. And we are going to use these partial labels to uncover the information about the lexical structure in the language. So we have a try bootstrapping training algorithm as follows. So the algorithm assumes for different word tokens, the underlying acoustic unit sequence should be the same. The algorithm is first for each word type, we go to the second for loop, consider each word token of this word type. And we're going to use the acoustic unit discovery model to decode each token and generate the one best acoustic unit sequence, like A25 and unit 30, unit 6, unit 10. And keep in mind each unit is associated with one sub-HMM. And we are going to create a word HMM model for this word type by concatenating the one best acoustic unit sub-HMMs. But in this case, when we decode different word tokens, it can lead to different word models. We're going to need a way to select one single word model. We use this approach. For each word token, we use the word model to compute the acoustic likelihood for this token. And we iterate for each token, and we compute the average likelihood by this model across each token. And in this way, we can select one single word model and use the model to accumulate the model statistics on all the word tokens of this word. The intuition here is we like a single sequence of acoustic unit models to capture and model the acoustic variations of different word tokens. We like a single sequence of acoustic unit model to increase the likelihoods of all the word tokens. And in return, when we use the model again to decode the different tokens, we expect that the model can give back the same single sequence of acoustic units. So finally, we updated the AUD model using the accumulated statistics from all the word types. So preliminary results, we have the AUD model. We have the AUD model with Bootstrap. Right now, by evaluating the normalized mutual information, the results stay the same. So we see the results on TIMate are preliminary and the challenges remain. we find some problem in the algorithm we just described. When we fix the word model for each word type, the creation of this word model is agnostic to all the other word tokens. So efforts are continued for more effective algorithm to consider the other hypotheses during creating the word models. In summary, we presented a strategy of using unlabeled word clusters as complementary information in unsupervised learning of acoustic models. And we presented an algorithm of bootstrapping bottom-up trained subword acoustic models using such top-down speaker-independent word constraints. And our efforts are continued for a more effective algorithm. We also consider metrics other than normalized mutual information, which can provide some insights to this algorithm. So we're going to see the next presentation by Ming to evaluate the acoustic unit by the same different task.